Okay, students. So now I'm going to discuss the exercise from your grade 10 science book, that is unit 12. We have discussed the lesson equilibrium of forces. You all know when there needs to be equilibrium, the resultant of all the forces acting on an object should be 0. So with that, we looked at different instances, equilibrium of an object under the action of two collinear forces in opposite direction. Then equilibrium under the action of three parallel coplanar forces and coplanar non-parallel forces. Thereafter, we also saw an example where there can be more than 2 or 3 forces acting on an object and still there can be equilibrium. So, from all those discussion, you can understand what equilibrium of force is, and you all know how to calculate the magnitude of forces acting on an object when there is equilibrium. So let's look at the questions. I am sure you have already answered them. If not, you all answer them first and then you can listen to the discussion. The first question. An object on a horizontal plane is pulled along a certain direction with a force of 20 Newton. So here you all know, students, you have to note these terms: horizontal plane, 20 Newton. Why does it have to be a horizontal plane? So it is just one plane. Only the effect of the force applied on the object will act on the object. There is no other effect. You all know if it was a slope, then that can lead to a change in the movement of the object. So that is why it has to be horizontal plane. In order to bring the object to rest, what is the force that should be applied on it in the direction opposite to the 20 Newton force? So this is what is going to happen. This is the horizontal plane. There is an object like this, and on the object there is a force acting with a magnitude of 20 Newton force. It says a certain direction, so we will consider that direction as this. And they say the force that should be applied on it in the direction opposite to the 20 Newton force. So what should be the opposite force? It has to be in this opposite direction. We'll say it is F, and you all know these two forces should have the same line of action. So they have to be collinear forces acting in the opposite direction. And for the object to be under equilibrium, what is the condition? The resultant force has to be 0. So that is what we need to consider here. For the object to be at equilibrium, the resultant should be 0. So when we say resultant, what is that equal to? We have the 20 Newton force in one direction and force F has to be in the opposite direction. So that is equal to 0. So what is force F? When we rearrange, we get the value as 20 Newton. Now this is the calculation, students. Even without doing the calculation, by looking at the diagram or even just reading the question, I am sure you will understand that the force has to be equal and opposite in magnitude. So here the direction has to be opposite. But according to the question, we only need to find the magnitude of force. That is, F is equal to 20 Newton. So I am sure you were able to answer these questions today. With that, I will move on to the next question. What would happen if a force of 25 Newton is applied on the above object in the opposite direction? So if we again consider the diagram, this is the object. We had a force of 20 Newton acting in this direction. Now they are saying what would happen if a force of 25 Newton is applied on the above object in the opposite direction. So if this force was 25 Newton. They want you to say what will happen. So just by looking at the diagram, what can you all understand? I'm sure you know they are opposite collinear forces. The magnitudes are different, so you know the object will move in the direction of the higher magnitude. So that is what is going to happen. We don't need to do any calculation. If you want, you can calculate the difference or the resultant force and you can include that in the answer. So here resultant force is going to be what? Now we need to consider the 25 Newton force first, minus 20 Newton. So that's going to be 5 Newton. So what will happen? The object will move in the direction of the 25 Newton force with a resultant force of 5 Newton. So that part is optional, students. You all can only write the object will move in the direction of the 25 Newton force. That itself is enough. Because here they have asked what would happen. So that's what they want you to do. But here, in addition to that, we have calculated the resultant force and I have included that also in the answer. I'm sure you all can understand that. And I'm sure you have already written the correct answer. With that, I will move on to the next question. The second question. If several people are trying to push a car whose engine is not functioning. So you all know this instance. If a car breaks down, we have to push the car to either move it to a side or start it again. So there are several people need to push the car. In what manner should each one try to exert a force on the car? How should they exert the force? Is it collinear, coplanar parallel or coplanar non-parallel? I'm sure you know the answer. It has to be in a parallel manner. So if this is going to be the car, so this is the car, each one has to push this way parallelly. On the bonnet, they have to push parallelly. So here it has to be coplanar parallel forces. It's not a must to draw the diagram. You all have to explain how they should apply the force. In what manner should each one try to exert a force on the car? Now, what will happen if they push each other? One person pushing the car, the other person pushing the first person. It will be collinear forces. There are also the forces will get added up. But still, it will be better if they apply coplanar parallel forces. All of them will be applying their force directly onto the car. And there are also the resultant will be the sum of all the forces. So here we can say they need to apply the force. Force directly onto the car in a parallel manner. So that is how you need to explain. I am sure you all have done that also. So with that, students, we will move on to the next question. The third question. If the resultant force of the two forces applied by the spring balances B and C as shown in the figure below is known, what should be done in order to bring the ring to rest? So we look at the figure. Here you can see it's a ring. It can be a metal ring or a plastic ring. And there are 3 Newton balances attached to it. So there they say Newton balances B and C. The resultant forces of the two forces applied by the spring balances B and C. So here B and C are two forces. They are going to be on the same plane. Are they parallel? No. They are non-parallel coplanar forces. So if the resultant of the two forces, what should be done in order to bring the ring to rest? If it was only these two forces, you all know the ring will move in a direction like this. Direction between the two forces B and C. So to bring it back to equilibrium or to rest, what should we do? We apply this force A in the opposite direction of the resultant of B and C, and it should be equal in magnitude. Then the ring will be at equilibrium. So that is what you need to explain here. If the resultant force of the two forces applied by the spring balances B and C as shown in the figure below is known. So we know those two forces. What should be done in order to bring the ring to rest? So here we know the resultant force. We can say a force equal in magnitude to the resultant of B and C should be applied in the opposite direction by balance A to bring the ring to rest. So the way it is shown in the diagram, between B and C, the resultant is going to be here. So this is going to be the resultant force, resultant of B and C, and that should be balanced by the force A, that is equal in magnitude and opposite in direction. So then the ring will be at rest. I am sure you all were able to explain this to them. So a force equal in magnitude to the resultant of B and C should be applied in the opposite direction by balance A to bring the ring to rest. So you have to mention both. The magnitude has to be same and the direction has to be opposite. With that, students, I will move on to the next question. Question number 4. A box is placed on a table. So you all know normally we keep boxes or other things on a table. Although the gravitational attraction force is acting downwards on the box. So the gravitational attraction or the gravitational acceleration, or what we call as the gravity, is acting downwards on the box. Why does it remain at rest without falling down? You all know the reason. We have looked at the diagram also. If we draw a diagram for this one, what do? We have the table like this. We have the box here. And there, the gravitational acceleration causes what? A force, that is the weight, equals m into g. Mass into gravitational acceleration gives you the weight. That is the force that is acting downwards. But the box does not fall down. Why? Because there is a perpendicular reaction. How do we write that? R. Perpendicular reaction. Or what is the other name given to this? The normal reaction. Normal reaction. What exerts this normal reaction? The surface of the table. When there are two objects in contact with each other, the surface exerts an force against the other object. So that is the normal reaction or the perpendicular reaction. And since the normal reaction R is equal to the weight, the object is at rest. They are equal in magnitude, opposite in direction. So that is what you have to write here. The box doesn't fall down, does not fall down because the normal reaction balances the weight of the object. They are equal in magnitude, and opposite in direction. So how do we call them? Collinear forces acting in the opposite direction. Collinear forces acting in the opposite direction. So if we look at the answer again, students, this is a diagram that is also optional. It's not a must for you all to draw it, but you all know when you draw a diagram, it's more clear. For the person who is reading the answer as well as for you all, it would be easier to explain. So here we have shown it. W is weight, R is perpendicular reaction. If you want, you can even write W weight. But you all know these are the standard letters that we use. So the box does not fall down because the normal reaction balances the weight of the object. And the two forces, they are equal in magnitude and opposite in direction. That means they are collinear forces acting in the opposite direction. So this covers all the required points. I'm sure you also have written a similar answer in your own words. So with that, students, I will move on to the next question. That is question number 5. What can you say about the nature of the motion of an object on a horizontal table that is pulled in opposite directions with two unequal forces? So here again, we can say there is an object placed on a table that is a horizontal table. So you all know why we call it a horizontal table or why it has to be a horizontal table. So that it's flat and there is no effect of the direction. You can easily apply the forces in opposite directions. So then there are two forces acting on it. There are two forces. One is F1 and the other one is F2. If we consider it that way, they are opposite and the forces are not equal. So F1 is not equal to F2. Then what will happen? The object will move in the direction of the higher force because there will be a resultant force. So that is what you need to write there. When there are two forces, they are collinear, so the line of action is the same. They are opposite, but because their magnitudes are different, there will be a resultant force. You all know if F1 was greater, we will calculate the resultant force as what? F1 minus F2. Then the object will move in the F1 direction. If F2 was greater, it will be F2 minus F1 and the object will move in the direction of the F2 force. So that is what is going to happen. So we have to say the object will move in the direction of the higher force. So, I am sure you all can understand that as well. When there are unequal forces. So, what can you say about the nature of the motion of an object on a horizontal table that is pulled in opposite directions with two unequal forces? That is what you have to consider here. They are opposite direction and unequal in magnitude. So, there will be a resultant force. The object will move in the direction of the higher force. I am sure students you have answered all these questions correctly, and that is the last question in your textbook. But I will discuss some more extra questions with you all related to the lesson. Extra question 1. The figure shows the two forces applied by two Newton balances attached to a metal ring placed on a horizontal table. So, when you read the question, students, I am sure you all know why each term is used there. So, there are two forces applied by two Newton balances. Here you can see that in the figure, that is the metal ring, and here you can see they are opposite to each other. And from the figure, you all can notice the two Newton balances are in the same line. So, that means they have the same line of action. And the way the balances are being attached, you all can see the forces are applied in the opposite direction. So, let's look at the question. What can you say about the forces acting on the ring when it is in equilibrium? So, you can see they have the same line of action. So, they are collinear forces acting in the opposite direction, and the object is at equilibrium. So, when it is at equilibrium, what can you say about the forces? They should have the same magnitude, so that the resultant force will be 0 and the object will be at equilibrium. That is what you have to write here. The forces have the same magnitude and what is it? Line of action. But act in the opposite direction. Therefore, the resultant force will be 0. Then the object or the ring will be at rest or equilibrium. With that, we will look at the next part of the question. A force of 5 Newton is applied towards a particular direction and a force of 3 Newton is applied towards the opposite direction during an activity. What can you say about this instance? So, if there is an object, a force of 5 Newton is applied in one direction. There is a force of 3 Newton applied in the opposite direction. What can you say about this instance? We have seen an instance similar to this. What can you say? The object will move towards the direction of the 5 Newton force. When there are collinear forces acting in the opposite direction but with unequal magnitudes, there will be a resultant force that will be towards the higher magnitude. So, therefore, the object will move towards that direction. So, I am sure students, when you look at the diagram itself, you can understand that. But we have to write it as the answer. What can we say? The object will move towards the 5 Newton force. So here students, if we go back and look at the questions, the figure shows the two forces applied by 2 Newton balances attached to a metal ring placed on a horizontal table. What can you say about the forces acting on the ring when it is in equilibrium? So what can you say there? You can say the forces have to have the same magnitude. It has to be the forces have to have the same magnitude and line of action, but act in the opposite direction. Therefore, the resultant will be 0. So then the ring will be at rest. And then if we look at the next question, a force of 5 Newton is applied towards a particular direction and a force of 3 Newton is applied towards the opposite direction during an activity. What can you say about this instance? So you can see the instance in the diagram and you know the object will move towards the 5 Newton force. Always it moves towards the greater force because these are again collinear forces acting in the opposite direction. So I am sure students you also gave a similar answer. With that, I will move on to the next question. Extra question 2. Draw a diagram to illustrate two forces that are equal in magnitude acting on an object in opposite direction. So they are equal in magnitude acting in opposite direction. That is what you need to show. So there is the object. You all can use any type of object. It's easier to draw a cube-like shape, a block that is easy to draw. And here we have one force. This is the other force. They will be acting in the opposite direction. Draw a diagram to illustrate two forces that are equal in magnitude acting in the opposite direction. So since they are equal in magnitude, we can label them as F. So here, since we have used the same letter F, that indicates the two forces are equal in magnitude. Instead, if you write F1 and F2, then of course you have to write and show that F1 is equal to F2. So either way, the diagram will be correct. So we have illustrated two forces equal in magnitude acting on an object in opposite directions. So with that students, I will move on to the next question. Extra question 3. Two groups of people are pulling the rope in the opposite directions during a competition of rope pulling. You all know rope pulling is also known as tug of war. Normally it's played during the New Year season. So you all know what happens there. The midpoint of the rope on which a red ribbon is tied is not moving towards any direction. So although the two teams are pulling the rope, there is no resultant force. That is why the red color ribbon that is tied to the midpoint of the rope is not moving. It's at equilibrium. Draw a diagram to illustrate the forces acting on the rope. So here, if we take this line as the rope, what will be happening? There will be a group of people pulling the rope in one direction. Another group of people pulling it in the opposite direction. The sum of all these three forces, if we consider that as F, the sum of these three forces will also be F. So that the red color ribbon, let's say this is the midpoint and that is the ribbon. So the ribbon is not moving. Why? The forces, the sum of all the forces applied by this group is equal to the sum of the forces applied by the second group in the opposite direction. So there is no resultant force. The ribbon is not moving or the ribbon is at equilibrium. I am sure you also would have drawn a diagram like this and you all can understand what happens there. So draw a diagram to illustrate the forces acting on the rope. It doesn't have to be 3. It's actually the sum of all the forces exerted by all the people. You can also just show one force in this direction and the second force in the opposite direction. That is also correct. But here when we write F, it is the sum of all the forces. I am sure you can understand that. With that, students, we will move on to the next question. Extra question 4. Specify the forces acting on a wooden block placed on a horizontal table. You are familiar with this instance. Again, we have discussed similar questions. So, there is a horizontal table. An object is placed on the horizontal table, or a wooden block is placed on a horizontal table. What are the forces? Always the weight acts downwards. And what is the force acting upwards? It is the perpendicular reaction, or what is the other name given? Normal reaction. Normal reaction. We can also use the letters. Perpendicular reaction is given the letter R and weight is given the letter W. So, W acts down, R perpendicular reaction is acting upwards. There are collinear forces acting in the opposite direction with equal magnitude. So, there is no resultant force. So, the wooden block is at equilibrium, or it is at rest. It does not fall down when it is placed on a table. You can also draw the table properly. Here I have shown only the surface of the table. That is more than enough to show it in the diagram. Then with that, students, if we look at the next question. Write an instance where an object is at equilibrium under three forces that are not parallel. So, object is at equilibrium under three forces that are not parallel. Can you think of an instance? A picture hanging on the wall, maybe a periodic table hanging on the wall tied with a rope. So, any similar example can be given. So, here I will say a picture hanging on the wall by a string attached to it at 2 points, or we can say 2 nails. There have to be 2 nails and the string has to be attached to that, and the string has to be like in a V shape, inverted V shape, and the picture has to be hanging. So, the weight will be acting downwards. The tension on either side of the string, there will be 2 other forces. So, altogether there will be 3 forces that are not parallel. So, that is an instance. Write an instance where an object is at equilibrium under 3 forces that are not parallel. A picture hanging on the wall by a string attached to it at 2 points. That is important. If it is just hanging from one string, what will that be? The tension will be acting upwards, the weight will act downwards. So, there are only 2 forces. So, those are 2 collinear forces in the opposite direction. So, that is why you have to say they are attached at 2 points. So, I am sure you also wrote a similar correct answer. With that, students, I will move on to the next question. Extra question 5. Write the conditions that need to be satisfied for an object to remain in equilibrium under the action of 2 forces. So, here you need to write the conditions that need to be satisfied for an object to remain in equilibrium under the action of 2 forces. What should that be? The forces should be equal in magnitude, they should act in the opposite direction, and they should have the same line of action. In other words, those are 2 collinear forces acting in the opposite direction with equal magnitude. But here we need to write the condition separately. So we can say they should be equal in magnitude, they should act in the opposite direction they should have the same line of action. So there should be 3 conditions. When we say they, I mean the forces. The forces should be equal in magnitude. The forces should act in the opposite direction. And they should have the same line of action. So you can either write as they or you can say the forces. I am sure you were able to write all these conditions correctly. With that, students, we will move on to the next slide. Extra question 6. The figure shows a book placed on a horizontal table. Denote the forces acting on the book. So this is a book placed on a horizontal table. They want you to denote the forces acting on the book. So you know this is a situation where there are 2 collinear forces acting in the opposite direction. I am sure you know them well. What are they? The weight acting downwards. So this way it's going to be the weight of the book. What causes the weight of the book? The gravitational pull or the gravitational attraction. So weight is equal to mg. And what is the opposite force? That is the perpendicular reaction or normal reaction. Perpendicular reaction or normal reaction. So those are the 2 forces. They both have the same line of action, opposite direction and same magnitude. That is why the book is at rest. I am sure you all mark these correctly. You can mark it as R and W or you can leave those letters out. You can just write the names, the weight and the perpendicular reaction, or you can use the term normal reaction. You don't have to always write both the terms. Here I am writing both the terms so that you become familiar with the terms. But you all can just stick to one term. With that, students, I will move on to the next question. Extra question 7. Use a diagram to illustrate the forces acting on a sphere suspended by a string. So we need to show the forces acting on a sphere suspended by a string. So if we take this as the sphere, it is suspended by a string. It is suspended by a string like that. So we need to show from where it is hanging. You can see the string and the sphere. What are the forces that will act on this? The weight of the sphere will act downwards. What will balance this weight? It will be the tension on the string. Tension on the string, that is T, and weight is W. So here you can see, students, the sphere is suspended by a string. Normally the string will be straight. Why? There will be the pull by the weight of the sphere, so that will act downwards and the tension will be upwards. So you all know both these forces are collinear forces acting in the opposite direction, and also they are equal in magnitude. That is why the sphere does not fall down. But if you cut this string, then there is no tension acting upwards, only the downwards weight. So the sphere will fall down. That you all know. So with that, students, I will move on to the next question. Extra question 8. Write the conditions that need to be satisfied for an object to remain in equilibrium under the action of 3 coplanar parallel forces. Under the action of 3 coplanar parallel forces. So, for an object to be under equilibrium under the action of 3 coplanar forces, what are the conditions that need to be satisfied? First one, they all should be coplanar. That means they should all lie on the same plane. What is the second one? The direction of one force should be opposite to the other 2 forces that are acting in the same direction. And the third condition is that the resultant of any 2 forces should be equal and opposite to the third force. So, if those 3 conditions are satisfied, the object will be in equilibrium under the action of 3 coplanar parallel forces. So, we need to write down the conditions. First one, the forces should be coplanar. The second one, the direction of one force should be opposite to the other 2 forces. And what is the third condition? The resultant of any 2 forces should be equal in magnitude and opposite in direction to the third force. So, those are the 3 conditions that need to be satisfied. The forces should be coplanar, that is the first one. The direction of one force should be opposite to the other 2 forces. And the other 2 forces, you all know, will act in the same direction. And the resultant of any 2 forces should be equal in magnitude and opposite in direction to the third force. So, if these 3 are satisfied, then the 3 coplanar forces will give rise to the equilibrium of the object. I am sure, students, you all have written all these conditions correctly. With that, I will move on to the next slide. Extra question 9. Write an instance of an object in equilibrium under the action of 3 coplanar parallel forces. Use a diagram to illustrate the above. 3 coplanar parallel forces, what are the instances you can think? A bunch of bananas or some heavy object hanging from a rod that is attached to a surface by 2 strings. An example that is given in your textbook. Similar to that, you can think of a rod that is supported on 2 supports where the weight of the rod is acting downwards and the reactions are acting upwards. So, similar to that, if you take a fluorescent bulb, if it is hanging from 2 strings or 2 wires or 2 chains, then that is also 3 coplanar parallel forces. So, they want you to write an instance and also they want you to use a diagram to illustrate the above. So, here I will say an object hanging from a rod suspended by two strings. So to draw the diagram, if this is the rod, it's hanging from two strings and that is the surface, and from that an object is hanging. So here if we denote the forces, this is the weight of the object and the tension. So tension, here there is another tension. So two forces acting in one direction, they are parallel, and the third force, the weight of the object, acting in the opposite direction and also parallel to the other two forces. So you all know three conditions need to be satisfied. All the three forces have to be on the same plane. We just answered that for the previous question. You all can remember that. So these three are all on the same plane. Coplanar forces, the lines of action are parallel, and these two forces are in one direction and the third force is in the opposite direction. And if you take the resultant of these two forces, that will be the sum of the two forces, that will be equal and opposite to the weight of the object. So that is how you show the diagram. So here it has to be an object hanging from a rod suspended by two strings. So that is how we show the diagram. I am sure you all have shown this correctly. So with that, students, I will move on to the next question. Extra question 10. A small rock is suspended from an object. What are the forces acting on the rock? What can you say about these forces? So there is an object. So let's say this is an object. From the object, a small rock is suspended. So this is the object and this is the rock. What can you say about the forces? Or before that, what are the forces acting on the rock? What are the forces acting on the rock? So here the force acting downwards is going to be the weight of the rock, W. And what is the force acting upwards? I am sure you know it is the tension. Tension T. So those are the two forces acting on the rock, the weight downwards and the tension upwards. And what can you say about these forces? What can you say? They are equal in magnitude and opposite in direction. So we can say they have equal magnitude and opposite direction. That means the resultant of the two forces is 0. But here the question is, what can you say about these forces? They are equal in magnitude and opposite in direction. So that is what you can say about the two forces. This is the diagram. From the object, a stone, a rock hanging from the suspended from an object. And here you can see weight of the rock is downwards, the tension is upwards, and this is the rock, that is the object. And the forces, they have equal magnitudes and they are opposite in direction. I am sure you also answered this correctly. With that, students, I will move on to the next question. Extra question 11. Indicate the forces acting on the following objects in equilibrium given below. So all the three objects are in equilibrium. Name the type of forces. So if we take the first diagram, we have come across almost all these examples. The first one, an object placed on a table, horizontal table. So what are the two forces acting on it? If you mark the two forces, the weight of the object and the normal reaction or the perpendicular reaction. So here indicate the forces acting on the following objects in equilibrium given below. So we have indicated the forces. What are these two? Two collinear forces acting in the opposite direction. That is the type of forces. So two collinear forces acting in opposite direction. Acting in opposite directions. Then the next one, you can see a metal sphere or a metal ball hanging suspended using a string from a certain surface. So there what happens? The weight of the metal ball again acts downwards and there is the tension acting upwards. Again, they are equal in magnitudes, then only the object will be at equilibrium. Same line of action, opposite in direction. So what is the type of forces? Collinear forces acting in opposite direction. So here, collinear forces acting in the opposite direction. That is the second type. Then what is the third instance? Third instance there, you can see this is like the manual balance. You can have a pan here, there is a pan here, it is at equilibrium. So what are the forces? Here we will have the weight acting along this, the other weight acting along this. Both of them will be parallel forces. So the weight W. And what is the third force? There will be a reaction acting upwards. A reaction. And they will be connected along this rod. So those are three coplanar parallel forces giving rise to the equilibrium. So if you are to write the type of the forces, those are three coplanar parallel forces. So three different instances. Here there are two collinear forces acting in opposite direction. Here again two collinear forces acting in the opposite direction. Then here we have three coplanar parallel forces. Here also we can mention that there are two collinear forces. Two collinear forces acting in the opposite direction. So I am sure students, by looking at a diagram, you will be able to identify what type of forces are acting on it and you will be able to mark the forces. With that, I will move on to the next question. Extra question 12. Some systems in equilibrium are given below. Again here there is equilibrium in the systems. What can you say about the forces acting in them? So if we take this first instance, you have seen this, the seesaw. I'm sure you all would have enjoyed playing on it when you were kids. So here you can see there are two kids, but you can see this child is sitting towards the corner, right towards the end of the plank, and this child or this boy is sitting somewhere towards the middle. You all know the reason. When we consider the equilibrium of this system, it has to be the moment of forces. So moment is going to be the force into perpendicular distance. If the force is less, we need to have a more longer perpendicular distance. If the weight of this boy is higher, that is the force is greater, then the perpendicular distance has to be short in order to maintain equilibrium. I am sure you all can remember that from the previous lesson. So here, what is this system? The weight acting downwards, the weight acting downwards, the reaction acting upwards. So if we mark the forces there, the weight of this child will be downwards, the weight of the boy will be downwards, and the reaction will be upwards. So weight, and the reaction. What is this system? 3 coplanar parallel forces. So here, what is this instance, students? You all can see a weight hanging. So the force will act downwards. This force will be acting downwards. Then what happens there? It has been suspended using 2 strings. The tension will act on the string like this. So those are 3 forces. They are all on the same plane, so coplanar forces. Are they parallel? No, they are coplanar forces that are not parallel. So here, 3 coplanar forces that are not parallel. That is what you can say about the forces acting in each situation. Then the third one. What can you say about the forces acting there? Here again, there are 2 objects hanging from they have been attached to the 2 ends of a string, and the string has been passed around a pulley. Normally, it's a pulley that is marked as A, and the pulley has been suspended from a surface. So, what are the forces going to be? In this, you can see the weight will act downwards, the weight will act downwards. So, the weight of the 2 objects. So, here since this is a M1, I will write that as W1. This is M2, so this is W2. So, the weight of the objects will be down, and you can see the tension on that string. So, what can you say about the 3 forces? You can see the lines of action of the 3 forces are parallel and they are on the same plane. So, those are 3 coplanar parallel forces. So, here these are 3 coplanar parallel forces. 3 coplanar parallel forces. The weights acting downwards, the tension acting upwards. So, these are 3 instances, students, that we see in our day-to-day life also. Similar to this, there are many other instances. So, when you look at a diagram, you should be able to identify the force, in what direction that is acting, and also what that system is. So, in this, these are 3 coplanar parallel forces. This is similar to the third one, again 3 coplanar parallel forces. But this diagram, again there are 3 coplanar forces, but they are not parallel. So, I am sure you all also mark the forces and identify the systems or the type of forces correctly. With that, students, I will move on to the next slide. That is extra question 30. Again, identify the type of forces acting in the systems given below. So, there are 3 systems. You all can see the first one, a person doing exercise. You know the monkey bars for exercise. But here, in this system, you can see the weight of the person will be downwards. Weight of the person will act downwards. That is always the case. Then, if you look at the hands of the person, they are wide apart. They are at an angle. So, there will be tension along the hands, but will that be parallel? No. Here the forces are going to be at an angle. Here, if we draw the diagram, the forces are going to be at an angle like that, and the weight will act downwards. So, the weight is W and the tension is going to be at an angle. So, again, the system will have three forces that are coplanar, but they are not parallel. So, if we are to identify the type of forces. So, three coplanar non-parallel forces. We can say non-parallel forces, or we can write as the forces that are not parallel. Either way, it's okay. But there are three coplanar forces acting on the system. Then if we look at the second example. What is this? A boy and a person, they are pulling a rope. So there what will happen? The boy pulls with a force towards this direction and the man is pulling it towards his direction. Just two forces, the same line of action, and they are opposite in direction. So here two collinear forces acting in the opposite direction. So two collinear forces acting in the opposite direction. That is this system. Then the third instance. Now this is somewhat similar to the first instance. Again a boy or a person hanging from a bar. There look at the person. Again, he also, the weight of the person will act downwards. Weight. Here what can you say about the hands? They are almost parallel. We can consider it as parallel. So then what will happen? Again there will be tension acting upwards. So if we show the three forces, here you can see they are going to be parallel forces. Three coplanar parallel forces. So these two, the first instance and the third instance, they are somewhat similar. The same instance, they are both two people are doing exercise on the monkey bars, but here the hands of the person are at an angle. So those are three coplanar forces that are not parallel. But here the hands of the person or the boy, it's parallel. So because of that, it becomes three coplanar parallel forces. So I am sure again you all can understand this situation. Here, although the boy's legs, they are far apart, but still the weight of the person will act downwards. So those are the things that you need to consider when you look at a system. So the first system, three coplanar non-parallel forces. Second one, two collinear forces acting in the opposite direction. And the third one, three coplanar parallel forces. So I am sure students, you were also able to identify them correctly. Then we will move on to the next question. Extra question 40. A poster made by a group of students is hanging on the wall as shown below. So this is a poster hanging on the wall. You can see it had been tied with two strings and the strings have been attached like that. So there are two forces F1 and F2 acting on the strings. Now we will look at the questions. From this you know the weight of the poster will always act downwards. We will look at the questions. What are the forces F1 and F2? What are they? They are the tension. Forces are the tension. So here the forces F1 and F2 are tension. Tension acting on the string. Then the second question. Mark another force acting on the poster in the diagram given below. So what is the other force? I told you all before. It is the weight of the object. Weight. We always use the letter as well. W. Weight of the object. So mark another force acting on the poster in the diagram given above. So that's the weight of the poster. Write the type of equilibrium that exists in the above system. There are three forces. They are all in the same plane. So coplanar forces, but they are not parallel. So three coplanar non-parallel forces. So three coplanar forces that are not parallel. So we can say that. You can say non-parallel forces or forces that are not parallel. Then the next question. Write two conditions that need to be satisfied for the equilibrium you mentioned above. Write two conditions. You all know, students, there should be three conditions. They have to be on the same plane, or they should be coplanar forces. They should not be parallel, but their lines of action should meet at one point. And also, the resultant of any two forces should be equal and opposite to the third force. Equal in magnitude and opposite in direction to the third force. So, there are three conditions. You are supposed to write only two conditions. So, if we write the conditions, the forces should be coplanar. Then the next one, the lines of action of the three forces should meet at one point. So here they should meet at one point, or in other words, students, you can write it as common point. So there are three conditions that need to be satisfied. The third one, the resultant of two forces should be equal in magnitude and opposite in direction to the third force. So you can write that as well. And I am sure, students, you were able to answer all these questions correctly. With that, I will move on to the last question of the extra questions. Extra question 15. The following figures illustrate two instances of equilibrium of three objects A, B and C. So, you can see in the first diagram, object A is at this point and B is there, and there is a plank that has been supported by a support, and you can see the distances between this point and A, it's 2x, and B and the midpoint is x. B and the support, it is x. So from this diagram, you all can get an idea. You can see it is at equilibrium. You are familiar with the moment. This side will be clockwise moment. This side will be anti-clockwise moment. So for equilibrium to happen, the clockwise moment has to be equal to anti-clockwise moment. And also you all know, when the perpendicular distance increases, the force has to be less. So when the perpendicular distance is less, the force has to be high. So from the diagram, you can get an idea the weight of A and weight of B. A will have a lesser weight compared to B, and that also it will be in a 2:1 ratio. If A was 1 Newton force, B will be 2 Newton force. Why? This distance, perpendicular distance, is 2x and this distance is x. So the weights have to be the opposite. A will be lesser in weight and B will be higher in weight. And if we look at the second diagram, there A, B and C all are shown. Already we know the weight of A and B. So what happens? A has less weight, B has more weight. Here A and B are placed together. So sum of the two weights, sum of the two forces, and here you can see the perpendicular distances are equal, y and y. So the weight of A plus B has to be equal to C, or the force exerted by A and B should be equal to C. So if we look at the question, the following figures illustrate two instances of equilibrium of three objects A, B and C. If the weight of the object A is 2 Newton, what is the weight of the object C? So if the weight of the object A is 2 Newton, what is the weight of the object C? So as I told you all, we need to calculate. We will take this as diagram 1 and diagram 2. So from 1, clockwise moment should be equal to anti-clockwise moment. To avoid the confusion, instead of this x, I will use the symbol as like this, 2x and x. So if we take the clockwise moment, that's going to be this one. What is that going to be? The weight of B into x. That will be equal to the weight of A, that is the force, into 2x. So here you know the value of the weight of A, that is 2 Newton. So 2 Newton into 2x. If we rearrange that, we can find the value for B. What is B? B is going to be 2 Newton into 2x divided by x. So x and x cancels off. So this becomes 4 Newton. What I explained to you all. Because this distance is double and that distance is half, the weight has to be half for A and double for B. So because this is 2x and this is 2 Newton, this is x, B becomes 4 Newton. That is the weight of B. Then we need to find the weight of object C. So what happens there? Instance 2. What happens there? A and B are together, whereas C is on the other side. There, of course, the distances are same. So, obviously, you know, the sum of weights of A and B should be equal to the weight of C. So, instance 2, if you want, you can write this and show. Then we can say, again, clockwise moment equals anti-clockwise moment. Students, you all might be wondering why we are discussing moment here. Although it is moment, from the diagram you can see these are systems of 3 coplanar parallel forces. So again, that is part of this lesson. That is why we are doing this calculation here as well. And most of your lessons are interconnected as well. So here it's C into Y is equal to A plus B into Y. So you all know Y and Y cancels off. C will be equal to A plus B, that is 2 Newton plus 4 Newton, and that's going to be 6 Newton. So the question was to find the weight of object C. So in the first instance, you can see A and B objects are there. From the ratio, you know A is lighter, B is heavier. So we found the weight of B using the equation where clockwise moment is equal to anti-clockwise moment. Why? This is in equilibrium. So from that, we found the weight of B as 4 Newton. Then we considered the second instance where A plus B was together. The perpendicular distance is Y. That was equal to C into Y. So from that, we were able to find the weight of C. So I am sure, students, you were also able to do this calculation correctly. Okay. So with that, students, I have come to the end of discussion on extra questions as well. So in this lesson, we discussed equilibrium of an object under different forces. Under that, we discussed the system where there were 2 collinear forces acting in the opposite direction, then 3 forces that were parallel and 3 forces that were not parallel, but both instances they were coplanar forces. And finally, we looked at an instance where there were more than 3 forces acting on an object, and all the calculations related to this lesson. So I am sure with the questions from your textbook as well as these extra questions, you all are able to answer any type of question related to this lesson.